session, I think. Um, I would like to introduce myself. So my name is Samiya, and I am a postdoctoral research fellow at the University of Wolverhampton. And most of my research work is around data science. So um, textual data analytics, numerical data analysis, or image data analysis. And most of my current work is around computer vision, considering the revolution that computer vision is. And I've done a lot of work in scholarly data. So that is what the second session would be about sequential learning and textual analytics. So if we just quickly go through the outline of this particular session, now what I would prefer, and I believe there's chat message. I hope it's not for me. If it's a message for me, please shout out because I don't really check chat messages while speaking. So right. So the format that I would like to follow, I don't know the generic format for the FDP here, but the generic the format that I would like to follow would be I will go through the presentation, and then I have a bit of an exercise around this. So they're just two use cases. So I can provide you with the Jupyter notebooks and the data set, and you can probably try that on your own. In case you have any problems associated with it, you can always come back to me. So as far as this particular session goes, the outline of this session is as follows, as you can probably see on your screen. So we'll start with a generic overview of neural networks. What are the popular neural networks? So feed forward, convolution, deep belief, recurrent. Um, I believe you would have a bit of a background about all of them, considering that you've been having sessions for like almost 3 days now. Then because computer vision majorly uses convolutional neural networks for the simple reason that they are the advanced neural networks designed for image processing particularly, and they work around all the challenges that are associated with MLPs, with multi-line perceptrons. So we're gonna take a look at the basics of convolutional neural networks, see how they recognize images, and how is it that they're different from how is it that CNNs are different from MLPs, and the different layers that are there in a CNN. So we'll just go through a quick architecture overview of CNN, and majorly what I would like to cover is the applications of CNN. So how is it applied, or where is it applied, and what are the possible use cases that you can look at from an academic as well as a research point of view. So if you're trying to push your research forward in computer vision, then what are the kind of possible use cases that you can look at? What is the possible experimental analysis that you can consider as far as computer vision and CNN-based image processing is concerned? So in that, we'll try and cover 3, 4 categories. So image classification, facial recognition, document digitization, and medical image computing. And finally, we'll look at the use cases. So what I'll do is I'll give you a quick walkthrough of the Python code that's there in the Jupyter notebook. And then I would like you to, in case I am not sure, and please correct me if I'm wrong, that would you be able to run Jupyter notebooks? Because I believe you've had hands-on sessions. So will it be possible for um, you to run Jupyter notebooks? Please shout out. I don't really know if you're writing or somebody's
Yes,
writing.
ma'am, we can do that.
Okay, so I will probably share the files at the end of the presentation, and I'll give you a quick walkthrough, and then you can probably run them to see just have a hang of the practicalities of everything associated with it. So that's a quick overview of what I intend to cover as part of this presentation. Now, to start with, as far as neural networks is concerned, now our daily lives right now, in the kind of world that we're living, we are surrounded with AI applications of all kinds. And with the rising use of social media and the way our lives are right now, pattern recognition, image recognition, object detection is something that most of the applications that we use on a daily basis on our phones use. For example, you have your facial recognition system with which you log into your phone these days. I mean, I don't even remember most of my bank passwords per se that I use for my mobile banking because it works in facial recognition. So that's the kind of dependency that we already have right now, and you can imagine the kind of dependency that we'll have in the future, considering the pace at which computer vision as a technology is going. So pattern recognition, object detection, image processing at the very basic level is something which is very, very, commonly used in application development these days, in product development. And the business side of things is what makes it very interesting, because when businesses are involved in some kind of an R&D, the progress is faster, the adoption is faster, and you get to see things happening on the ground, in the air and everywhere around you, rather quickly. So that is what is the buzz about artificial intelligence, and is the buzz about computer vision as well. The whole rise and shining aspect of computer vision is attributed to the fact that it's very commonly used in most of the applications that we use every day. Now, the very fundamental and the foundation of artificial intelligence lies in the fact that we're trying to train systems in the way that humans are trained, in the way that human brain is trained. So we're basically simulating the human brain. We're trying to simulate something that even we don't understand very well, but we are trying to simulate the human brain in a way that we can make machines learn and adopt learning patterns. Now, as you probably know, that humans learn at different levels. So it's not just about knowledge-based learning; it's also experiential learning. It's a combination, a hybrid of both sometimes. So the whole pyramid of how data science evolves from data to information to knowledge to intelligence, and then finally to wisdom, which is what we are targeting in terms of research in artificial intelligence. We're trying to bridge the singularity between machine intelligence and if somebody's mic is on, can I please kindly ask you to mute yourself because it's a little disturbing. So yeah. So what we're trying to do at the research level in artificial intelligence is we're trying to bridge the gap, the singularity between machine intelligence and human intelligence. And for that, what is most important is to understand the different learning methodologies that humans follow, and then adopt that or implement that or deploy that onto routines in such a way that they can uh, have knowledge-based learning, they can adapt to experiential learning, and then archiving experiential learning into a format that can go sit at the back, sit in the back seat as knowledge-based learning. So cumulatively, intelligence is where we are at right now. Wisdom is what we are targeting. So that's as far as a generic AI overview is concerned. Now, brains, not just human brains, but even animals, like, for example, if a dog typically recognizes its owner, or most animals would, I mean, cats and horses would recognize that you are the owner and somebody else is a stranger. Or what is the, I mean, as far as recognition goes, uh, brains have that kind of an image, video, audio, cumulative processing ability that we are trying to implement in parts, in machines. So, how is it that you would typically ask a child, or train a child to identify the difference between an apple or an orange? So what you typically do is, if it's like very young, a toddler, you would show that particular object and say that it's called an apple, or this one's called an orange. And when you do this repeatedly, the brain automatically trains itself to identify apples and um, oranges. Now, if you give a child, a toddler, a green apple, initially that'll be difficult to understand and you'll have to retrain the model. So that's how basic training and retraining and intelligence works. That's at the very core of the non-technical aspect of artificial intelligence and learning and representation of objects and data. So what is a generic um, know-how of what's happening around you, the context, which is generally associated with videos and audios. That's actually an personification of a human experience. So when we say social media has unstructured data, has a lot of videos, has audios, has pictures, images, text, that's a personification, actually, an impersonification of our lives in a way. Because when we communicate, when we look around, that's like that's the voice and the video and the natural language, which is the text that we use, and different countries use different language and different dialects. So that's basically all of it being scaled down in the form of a social media context. And that is how learning, human learning, directly translates into machine learning or deep learning. Machine learning in a pre-context and then deep learning as we go forward. Now, on a more technical term, artificial neural network is basically a computation system. So it basically attempts to mimic, like I said, it attempts to mimic how the neural connections in the nervous system of the human brain are. And like the human brain, like I said, there are many layers of learning and different forms of learning. So there are many layers that a neural network has, and the structure and the function of the human brain is simulated in machines in the same manner. And I mean, the trial is such, we attempt that. It's something that we may or may not be able to do, but that is something we're trying to simulate. Now, the challenge here is that because human brain has the capacity to deal with a hell lot of data. I mean, ever since you were probably born, you've collected so much of data. Some you remember in your active memory, some you remember in your passive memory, some you have to be reminded about, some you don't remember at all. So humans have this. I mean, we've been blessed with that kind of a memory computation processing system infrastructure in something as small as our brain. But in machines, now we need to design all of that. We need a storage a capability that can allow that kind of data collection, data handling, data processing, uh, the different complex algorithms associated with processing of information, which our eyes just usually do. I mean, you look at something, you identify it's a dog, or you identify it's a tree. That's the kind of processing that we automatically do. Now, for us to be able to implement that kind of a processing in a system, it involves a lot of complex algorithms. And now, if we have to implement them, process them in real time, the computational capabilities of the system, the storage capabilities of the system have to be extremely high, and it's overwhelming for traditional infrastructures to support that kind of. Okay, if you can wait for a minute, I can see a few messages. Okay. So that's basically what the challenge is with neural networks. Now, if I go to the next slide, now there have been many neural networks. We started with the standard feed-forward neural network, which was like the multi-layer perceptron model, where we were trying to mathematically model a neuron, the way it functions, how it activates on the basis of as soon as it reaches a threshold value, it activates and deactivates and so on. And that's how most of the operations associated with our brain happen. So the initial part of research in artificial intelligence has been mostly around mathematically modeling the neuron. And now it's not just one single type of neuron that does everything. There's no one size fits all. So we are trying to mathematically model all of those different functionalities in such a manner that we can implement them into physical systems. Now, initial part of work, like I said, MLPs was mostly around understanding these threshold values and understanding how we can activate a neuron and how the whole layered structure can possibly work. So where are these layers going to be? Are there going to be different kinds of layers? What are they going to do individually? How are they going to progress individually? So all of this is specifically part of the feed-forward neural network. And the basic task that it used to do, coming from machine learning itself, which basically does two things: classification and regression. Like that's like the most basic thing that we teach students doing data mining. That you just need to do two things: it's classification, and you need for categorical data, and for numeric data you do regression. So initial work in neural networks was mostly focused around these two categories. Now, as we move forward and we looked at, and the advent of social media has had a lot of impact on this, particularly in the sense that we've had access to digital data in a way and at a pace that we never had before. So now that all of our research is focused around, getting feeds from Facebook, which now is not legally legitimately possible, but it was possible some years ago, or doing hashtag analysis on Twitter, where you have APIs available with most of these social network portals, and you can, possibly get the data from there, crawl data, or I mean, any which way, get the data and analyze it. Now, that has brought in a lot of challenges in the sense that the whole activity around collecting data at a pace which is almost real time, if its collection has to be real time, processing has to be near real time. We're yet to achieve real time visualization in terms of research, or as far as data visualization is concerned. So all of that has actually brought around a lot of challenges regarding processing of data. So that is where advanced algorithms and advanced neural networks came into being. So we needed systems that could um, specifically process images. Now, what was the problem that we had with the previous network? Why is it that it was not able to do it, or not able to do it effectively? It's something that we'll look in one of the future slides. And so convolutional neural network was a network that was specifically designed as an advanced form of neural network for image processing, for image classification and object detection, and all of the other applications, the whole umbrella of applications that follow as part of these two. Now, the second type was recurrent neural network. And the reason why we needed a different recurrent neural network, or something different from convolution, is both of them work on very different paradigms. They work on different mathematical philosophies. Recurrent neural network basically is for textual processing. And as you know, as I speak, if I speak in a specific order, you will understand what I'm saying. But if I jumble up the words, you will have to process it at your end. You'll have to first acquire it and process it, and then you'll probably be able to understand what I'm trying to say. So the specific characteristic of textual data, where it needs to be in a sequence. Alphabets need to be in a sequence to form a word. Words need to be in a sequence to form a sentence. And sentences need to be in a sequence to form paragraphs and complete text for them to make sense. Now, this basic characteristic of textual data is what makes it so complex to understand and process. So for this kind of processing, where you should be able to maintain and learn the sequence of how alphabets, how characters are coming in, how the words are coming in, how the sentences are coming in, all of this cumulatively forms a big corpus of a research field in itself, which is natural language processing. And the backup processing capabilities, as far as neural networks is concerned, is provided by recurrent neural network. So as you can see here, there are a few generic applications which are natural language processing, time series prediction. Time series prediction, again, why? Because it has to be a sequence. The next value is dependent on the previous value. And the next value in its discreteness would make no sense until and unless you know the previous value. For example, stock exchange data. If I tell you the value of the stock was this at this time, and it was this at this time of the day, and I don't tell you about the context, what it was before or after, then there's no trend that you can analyze. There's no kind of prediction that you can do. It has no meaning. It's like just a raw fact that would not affect you in any way. So that is why in time series data, whether it's weather data or stock market data, financial prediction data, all of these are cumulatively, I mean, the examples of time series data, and all such applications that require a sequence to be maintained require recurrent neural networks. Uh, Speech recognition, again, if you look at speech, it's basically a natural language that you're speaking. So any system would basically just acquire this speech, convert it into text, and then process it. So that's the most intuitive way of processing speech in any format. And if you can probably come up with something better than that, then that would be novel in its own way. But natural language processing in terms of speech is that's how it happens. Again, because it's natural language, it needs to follow a sequence, and because it needs to follow a sequence, we need a neural network that can learn that sequence, that can understand that sequence. So recurrent neural networks again. So these are the most the popular neural networks that are commonly used. And as part of my sessions, for this particular session, I am mainly going to focus on convolutional neural networks. For the next one, we're going to look at recurrent neural networks. So let's see if there are any messages. Okay, none for me. Okay, moving on to the next slide. So coming to the main agenda, convolutional neural networks. So the word convolution, and because computer science is basically applied mathematics, it's mathematics at work. So convolution, and most of the terms actually come from mathematics. So if you de-abbreviate most of the complex technological abbreviations that we have in computer science, they all come from mathematical terms. So it's less of engineering and more of mathematics. So if we talk about convolution, it's basically a mathematical function that is derived from the integration of two distinct functions. So what is it that you're trying to do? In very layman term, you are trying to see the effect of one function on another and seeing them as a whole, cumulatively. So that's, I mean, to define it, a convolutional neural network is an artificial deep learning neural network. And it basically works on the fundamental principle of convolution, which is a mathematical function derived by the integration of two distinct functions. Now, the primary task that we try and do using CNNs, using convolutional neural networks, is we try and classify visual content. We try and recognize specific objects in an image, and we try and gather them into clusters. Now, what is it that I mean by this three? It's pretty, I mean, it's pretty simple to understand, but I mean, just to give you an example on why and hows is if I give you an image and I ask you to recognize, say, faces, just faces, or if it's like, if I ask you to recognize all the circles and triangles and rectangles in an image, irrespective of what their meaning is. Just like we ask toddlers to do at preschool, that find all the things that are triangles or find all the things that are rectangles. And that's the first thing where we try to classify visual content and say that, well, this is this particular specific type of a thing. So now if we talk in the social media context, and if there's, say, an image from a conference, a picture with like, I mean, the pictures that we generally take at conferences where you have the whole, like 100 people who came to the conference and there's like a common picture. In the pre-COVID times when that was possible. So a picture typically had many people in one picture. So the first thing is classifying visual content. So humans will be classified. Okay. The second thing is you recognize uh, objects within that image. So if you look at the application that Facebook has, where you can actually tag people, so it gives you a recommendation on who possibly that person is in that image. Now, if it's just one person, I mean, it's not such a hassle, but if it's like a conference picture where you have some 10, 20 people standing in one picture, that is really helpful. I mean, you can just directly tag people with these suggestions, and it's much simpler. So recognizing every single person, recognizing that it's a person is the first thing. Recognizing who is that person is the second thing. Now, third is gathering them into clusters. So recognizing all of those people cumulatively. So it's not just one single person. So if you see it at a very, very naive level, then when you're trying to recognize a person, what are you trying to do? You're basically trying to identify a structure which cumulatively has a face. Now, face will have a subset like eyes and nose, and will have a jawline and the edges. So you basically identifying basic structures. That's when cumulatively you identify that, that's a face. Now, who that face belongs to is the second part of it. Now, identifying this thing for many people is a cluster of objects that you need to gather information about. So these are primarily the three kinds of tasks that CNN does. Now, going on to the different layers of CNN and how it basically works is, if as you can see here, because it's basically, I mean, based on convolution, like I mentioned in the previous slide. So convolutional layer is the primary and at the core of CNN. So basically, it identifies identification for you. So specific things that you're looking at, like in the example that I mentioned. So identifying hands, or identifying mountains in the background. So all of those are specific features that you, so for example, if you have an application where you want to cluster all the images of hills in the background, then that's the feature that you will have to identify. So that kind of a task is something that's done by the convolutional layer. Now, second is a rectified linear unit layer, or ReLU as it's commonly called. The objective of this layer is to increase the non-linearity of the image. So what we're trying to do is we are trying to strip the image of anything that's not relevant to the application. So like I said, if I have an application where I want to cluster all images with hills in the background, then anything in the foreground is not of interest to me. So I can just get rid of all of those. I can just have the image with the hills, or just look for hills and strip the image of anything else that I don't need to process. Now, why we do things like these is because I mean, our machine, our physical systems, the machines are not as capable as our brains. So it cannot really do that kind of a processing or computational complex tasks in the required time. So we need to give it the minimum that it requires. We just need to give it the things that it requires to give us the output that we need. So anything that's in excess, anything that we don't require, like going back to the conference image, if we just need to identify faces, tag people, what's in the background is something is of no value of us. So stripping the image of anything that's not important is done by the ReLU layer. Now, the next layer is the pooling layer. The objective of the pooling layer is to reduce the number of parameters. So basically what it does is regression in a way. It identifies parameters that are specifically relevant for your task. So in the last, in the ReLU layer, what it did was it stripped all the fat of the meat. And now what we are doing is now we are focusing on what we have got for analysis. So enhancing or understanding what we have for analysis in a better way is what the pooling layer does. And finally is the connected layer. Connected layer is something that we have inherited from MLPs, from multi-layer perceptron model, or the basic, what we call the basic artificial neural networks. So it's just like a completion layer. We need it because we need to complete, it's like the finishing line. We're waiting for things to complete so that we have a cumulative result in place that can be presented to the user. So that's what the final fully connected layer does for us. Now, looking at a specific, I mean, I would say classes of applications, because applications is something that's like huge. So classes of applications, the first one is image recognition, and image recognition is one of the typical applications of CNN, and one of the typical applications that are used in a lot of computer vision based applications, whether that's, for example, if you are working on surveillance systems, UAV based surveillance systems, or you're using drones for, say, monitoring a football field, or you're using drones for agricultural purposes, where you have drones, 5G connected drones that can monitor an agricultural field for any kind of intrusions, for any kind of even as something as minute and as minor as capturing the video and the images of the plant, which can then further be processed and used to predict if the plant has any plant disease or anything like that. So all of these are where you are trying to recognize an object and then focus on that object. Like I said, first you recognize the object, then you understand what the object is, then you contextualize what you're trying to understand, like we did in the pooling layer, where we're trying to enhance the meaty parts, we're trying to understand what is in the focus more. We're trying to gain better understanding of that. And finally, that's how, once you contextualize it, that's when your application gets the value that it does. So that's a typical workflow of a computer vision application, and where image recognition fits into it majorly. Now, as far as how and the different steps as far as image recognition are concerned, goes. Now, the first part is that the convolutional neural network basically has to perceive an image. So it, in all probability, and that's something that we understand from the very basics of image processing, is it's a volume, it's a 3D volume that the machine sees. So it's an image as a volume, a three-dimensional object. And typically, because generally, it's if we talk about real life videos, like drone based surveillance of agricultural fields, for example, they're going to be colored images to process. So they're typically in the RGB format. So other than just the every pixel that we expected to process, we are expected to process 3 channels of this. So it's multiplied further. Um, Now, what that basically means is that the convolutional networks need to understand that every pixel and the whole image will have these 3 channels stacked onto one another, and then will need to process these on the basis of these parametric values. Now, what CNN basically does is that it groups pixels and processes, and puts them through filters. So what you basically do is you recognize geometric shapes of an image, and then you apply a number of filters to it. And depending upon the complexity of an image and the purpose of recognition, you would need to identify the filters or the techniques that need to be applied. Now, the pooling layer in this case would perform regression, again reduce the number of parameters, in the sense that it will allow you to identify what is the specific characteristic that you're looking for in that image. So as a result of the whole processing, what you get is you get a recognized image by, if for example it's a tag feature on Facebook. So you identify the different features of that particular face, identify the credentials associated with that face, and then this kind of an association property is what lets you, make suggestions of who can that person possibly be. So that's about image recognition. And now let's just take a, a look at kind of a problem statement that typically follows this workflow. So what I have here on the screen for you is the images of us. It's an image of a swan, as you can possibly identify. Now, if as a human, uh, I ask you, if you come from, I mean, if you come from a country where you've not had a chance to, I mean, look at swans that much, then you might have difficulty in identifying a swan. But for the basic training, the learning model of humans, that's how it works with machines as well, is you identify some basic characteristics associated with the image. So what my task is here is I am trying to identify a swan. So I want my system to be able to identify a swan. If I give it 100 images and ask it to cluster all the images that has swans and that don't have swans, it should be able to do it. So at the very core, what is it? It is object detection. It is image recognition. So um, first thing is what are you need to define the characteristics, the features that you're looking for. So typically a swan would have white, pale white color. It'll have a long neck. It'll have a beak. And I mean, if you go into a little more details, it'll have black colored tail legs and and an oval shaped body. Now that's simplistic. That's, I mean, that's a standard swan picture that is majorly available. Now, if you train your model according to this, you should be doing fine with images that look like this. Now, what if your picture or the image that you get or the system gets looks something like this? The features are the same. There's a long neck, there's a white, pale white colored body. You have the black legs. You have an oval shaped body. The problem is that it's much more complicated to understand these features in this case. So it's not as simplistic here. Now moving on to the next. Now, what if it's even more complicated? What if you don't have all the features? Can you still identify if it's a swan? For example, if you see the image on the left, um, the oval bodies are still there, the white pale white colors are still there, but the neck is folded backwards. So you can't really, I mean, it's not so simplistic to identify the long neck that we've been defining all this while. Or if you look at the image on the right, then you can just see eyes, and you can vaguely identify a beak and a part of the long neck. So it's not, again, not as simplistic as the standard swan picture that we saw in the first slide. So identifying this to be a swan or this to be a swan will not be as simplistic as identifying the first picture. Now, until now, we had the white, pale white color, but swans can be black too. So what if the color changes? Will your system be able to identify that? So variations is what we're talking about, variations in features. How much of a variation is allowed? How much of a variation can you actually allow on your system? Or if we complicate it even more, it might not even be a swan, and it might have the shape of a swan, like a water balloon, or a swan shaped tent, for example, or a swan that's curled up, or it's just a part of the swan's body is visible in the image. What if you have images like these? Can your system still be able to identify or recognize if it's a swan? Typically, because I mean, we are humans and we give ourselves the leverage to say that, all right, we're humans, we can make mistakes, we might not be so accurate, our accuracy will not be 100%, and we are allowed to make mistakes, but we expect our systems to be 100% accurate, and we strive for accuracy that is as close to 100% as possible. So at the learning level, that thing is possible only if you train your model in such a way that you have covered all the variations, you've covered all the exceptions and everything associated with it. So now that we are done swanning and we've seen quite a lot of swans, let's come back to artificial intelligence again. So if we talk about neural networks, for example, what we basically have to do at the system level is we need to detect features in these images. And at the very, very naive level, if we go to the first image that I showed you, we need to identify those three things. If it's a long neck, an oval body, white pale white color, then we say it's a swan. Otherwise, we get into a state of doubt where we investigate further. So that's the most naive way of putting it. Now, in order to solve such challenges that I showed you in the last few slides, the variations in features and how all of them converge to the same definition of a swan. A swan remains a swan, but how the swan will be in an image is different. So understanding those variations and learning those variations, the complexities associated with these variations, there have been several models and algorithms and approaches designed for this. And people have come up with all kinds of computer vision techniques like SIFT and FAST and SURF and BRIEF and very many of these, including hybrid approaches and extended approaches of these. Now, again, the problem is that we either make approaches too generic or we over-engineer them. So what happens is they are either too generalized or they're too simplistic, and they don't work on all the exceptions, or they work on some of the exceptions. And there is human intervention and required and involved in training the model, at the data level, at the data set level. Now, so what is it, if we cumulatively analyze the problem and see what is it that we require? Now, we need a system that can automatically learn the features that it needs to identify. So it's a form of a representation learning or feature learning, as you may call it. So that is what we need our systems to support in order to understand and possibly have a highly accurate, if not a perfectly accurate system to do this. Now, if we talk about representation learning is an established field which generally talks about techniques that allows the system um, to automatically find relevant features for a particular application or a task. And it's generally designed to replace manual feature engineering. So if you know about manual feature engineering, your generic machine learning methods like k-means and PCAs and dictionary learning, all of that. So now how we are trying to implement representation learning or feature learning is using neural networks. And what are neural networks we're using? Convolutional neural networks. Now, before we can do that, what we need to understand is what is wrong with the traditional neural networks. Why is it that we cannot use traditional neural networks and we need a more advanced version of it? Now, assuming that you have some background about multi-level perceptron, and if you don't have, then the basic fundamental about it is that, like I said, it's based on the concept of human brain. So we're simulating human brain. At the very core of the human brain is neurons. So the brain fires neurons for all kinds of activities, everything that we possibly do, as every humanly task that we possibly do, and even the ones that are not humanly. So at the very core level, all of these basic neural networks were just modeling that neuron mathematically. So what they were doing is they were mathematically modeling the neuron, and it was present in a connected node network format. So like you can see probably on the screen, it has to flow from one node to the other. So there are nodes involved. The neuron is activated once a threshold value is reached. So these are the two main characteristics. One is it's a connected node system, and neuron is an entity which is mathematically modeled to activate itself when the threshold value crosses. Now, there are several drawbacks of this particular approach particularly when we talk about image processing, in the sense that, let me just check, there are a few messages in the chat. I hope none are for me. Okay, right. Okay, so there, as far as the traditional neural network is concerned, there are some drawbacks when we come to image processing, particularly in the sense that because, like we said, multi-layer perceptrons basically use a single perceptron for every input. In our case, we are processing every pixel, but then every pixel is in the RGB scale. So there are 3 channel inputs. So now the amount of weights that we need for larger images, so as the number of pixels increase, the weights that we would possibly require would be, I mean, for example, if you take a 224 by 224 a pixel image with 3 color channels, the number of weights that you would require to train would be 150,000. So that's the kind of difficulty that arises when we're trying to train these models, and there's a higher chance that they will overfit. So these are the main drawbacks that are associated with the use of MLPs for image processing particularly. Now, if we can move to the, yeah. Now, another problem that occurs with MLPs particularly is that they react to different input images differently, in the sense that if I have an image, if I just, for example, if you can see the image on the screen, it's possibly the same image. It's just that the position of the cat face has changed a bit. Now, if we talk about MLPs, the MLP will train according to the weights calculated for the first image. When it gets a second image, it will update the weights. So assuming that all the images that we'll get in the future will have the cat image face uh, right where it is in the second image. So that is the problem with MLPs, that, you know, if as soon as you shift an image or you change the image form in any which way, keeping the sanctity of the image intact, um, it retrains itself. It tries and corrects itself, and it tries and assume that every future image will have to be like this. And if it's not like this, then it retrains itself again. Now, this is why MLP is probably not the best thing to use when it comes to image processing. Now, another important problem is that, you know, particularly when we use MLP for image processing, is that the image is flattened and some of the spatial information is lost in the process. So it's important for image processing in a lot of ways. And if for people who've already worked in image processing would know that in order to process every single pixel, it's necessary to look at the neighborhood in order to perform advanced image processing, which is something that MLP cannot allow you to do at the very core level, which is the reason why we need advanced, one of the reasons why we need advanced neural networks to process images. Now, coming to how and what changes with CNN. What changes with CNN, and I hope the case is clear why MLPs are really such a terrible idea for image processing. CNN manages to solve most of the problems. As you can see here, one of the advantages, and like we said in the previous slide, neighboring pixels need to be considered, is something that CNN can do because it's not working on a single perceptron like the MLP. And objects are, you know, not cumulatively identified, they're identified in parts. So even if a part of the image is there, like a part of the swan's head is in the image, you can still identify that it's a swan. So that kind of functionality is possible with CNN, which is typically not possible with these standard neural networks. Now, if we analyze the influence, I mean, just to give you a broader idea on analyzing the influence of nearby pixels, particularly in the context of the use of filters, which is very common in image processing. So a filter is exactly what you think it is. It's, I mean, in our situation, we take a filter of a size, say, I mean, typically it's 3 by 3 or 5 by 5, and we move this across the image from the top left corner to the bottom right corner. Now, for each point in the image, the value is calculated on the basis of the filter using the convolution operation. Now, a filter could be related to anything. It can be pictures of humans. It can be associated with just identifying noses. It can be identifying just pairs of eyes or pairs of ears. So any particular thing. In addition to just identifying that, it's also identifying the location. Now, if it's just the location that has changed, it should not really change a lot in terms of the features of the image, until and unless that's something that you're looking at. For example, if you are analyzing a video where you are tracking a particular, say, if it's a football match, if you're tracking a particular player, then the player remains the same. You're tracking the position. Position becomes significant then. In the cat image that I showed, if I'm just identifying if there's a cat in the image or not, irrespective of where the cat is in the image, um, location isn't really important. So what we need is we need information both about the image and about the location of the image. Now, coming to what it does for you on a more technical side of things, it reduces the number of weights that the neural network must learn compared to the MLP, because you are actually keeping track of the location. So if the location has changed, you don't need to update the weights like we were updating for MLP. So that reduces the complexity. And any kinds of feature changes, particularly that are observed in the scenario where a location change has occurred, uh, and that, I mean, that's something that throws MLP off really badly. It's something that will not happen with CNN. Now, if you are wondering in the present context, in the image that you can see on the screen, how is it that the different features are learned by the network, and whether it is possible that the network will learn the same features, like, I mean, if there are 10 people, and 10 people would mean 10 pairs of eyes, 10 noses, etc. It should be able to identify a nose, and it should be able to cluster them together. Identifying 10 different noses makes no sense, and it's something that's just increasing the complexity of the task, which is more of redundant. So it's highly unlikely that you'll be using the same set of filters for the same set of tasks over and over again. Now, just to give you an example of filters, or kernels as they're called, as you can see here on the screen. Now, once an image goes through a filter, what you get is a feature map, which is generated. They're then taken through an activation function, which decides whether a feature is present at a given location in the image or not. Then with that, we can do a lot of things, like we can add more filtering layers, we can create more feature maps, we can create a deeper CNN for more complex applications. We can also use pooling layers for improving the feature map values and the kinds of inputs that we are getting and putting into subsequent layers. Um, and finally, I mean, there are many kinds of operations that can be done at the pooling layer level. However, what is the generic practice is we use max pooling, because mostly in the kinds of applications that image processing or video processing requires, we're looking for anomalies. So max pooling is what is generically used. Now, here is a sample CNN for you. As you can see, there are two convolution layers, two pooling layers, and a fully connected layer. And as you can see here, that's the kind of sequence that's followed for general image classification type applications. Now, just to give you a quick comparison and reiterate how MLP and CNN are different, MLP, what it cannot do is it does not scale well for images. It ignores the information brought by pixel position, and particularly in correlation with the neighborhood pixels of a particular pixel. And it cannot handle any translations or shifts in terms of the position of the image. Now, the general idea of CNN is to intelligently adapt to this and adapt to these properties of images where you can have the object that needs to be identified at different locations, and there may be variations in the features that you've decided. So, pixel position and neighborhood have semantic meanings is something that CNN better understands. Then the elements that are of interest can be placed anywhere in the image is again something that CNN better understands. Now CNN apart from the generic layers that we talked about, has the fully connected layer as well. So you basically, what you do is you create 2D slices of the filters called kernels, and these filters introduce translation invariance and the parameter sharing. And how are they finally applied into the image is convolution. So that's what the mathematical operation and the mathematical modeling of this particular model holds at the base, at the core of this neural network. Now, one thing that you might want to ask here is what happens to the edges now that we have applied a convolution on the normal image. The result will probably be a downsampled image, which will be the size of the filter. So how do we do this? We do this using a technique called padding, which is something that you can look up. I mean, if you're interested, it goes into the advanced forms and the advanced approaches used for computer vision. Now, looking at how do we connect our filters together. So how is it that we apply convolutions to images? Now, if we have many feature images and we need to combine them into a network to get our final results, how do we do it? Now, because we have multiple filters, which will typically be the case in most of the applications, that you'll not have a single filter, you'll have multiple filters. So what you'll end up with is a 3D output, a one 2D feature map per filter. So because you're having multiple filters. Now the feature map dimension can change drastically from one convolution layer to another. You can actually enter a layer with a lower dimension input and exit with an output with a much higher dimension because of the number of filters that you've applied. Now, convolving the image with a filter produces a feature map that highlights the presence of a given feature. So that is what is the output you're looking at. Now, in a convolutional layer, what we're basically doing is we applying all those filters in the convolution layer. Like I said, how do you apply those filters? You apply those filters using convolutions. So convolutional layer is basically responsible for applying the filters over the image to extract different features. Now, the problem is that how will you learn these features? So that is where non-linearity comes into play, and that is where the ReLU layer comes into play, where you perform all of those kind of non-linearity. It's the non-linear unit present in a rectified non-linear unit present in the CNN, which combats the vanishing gradient problem, which generally occurs with sigmoids. Now, if we if we make a quick comparison of the different layers that are there in a CNN, uh, typically, other than the fully connected layer, which is something that we inherited from MLPs, we have three main kinds of layers, which is convolutional, ReLU, and the pooling layer. Now, all of these different layers, basically, convolution layer, to reiterate, are the filters that are applied to the image, and all the other feature maps that are there in a deep learning setup, an artificial neural network like a CNN. This is where most of the user specified parameters are in the network. All the parameters that you do for finer tuning of the neural network are given. and given as input to the convolutional layer. And the most important parameters here are the number of kernels and the size of the kernels. Now, the second I mean, other than the ReLU layer, which is something that we extensively discussed, is the pooling layer. Pooling layer is very similar to the convolutional layer, but they perform very specific function. For example, like I said, you define max pooling for outlier detection. If that's something that you're looking at, there are other kinds of operations that you can do as well, like average pooling, for example, which takes the average value of the filter region. So all of this is typically, I mean, the objective of doing all this is to reduce the dimensionality of the network. And finally, I mean, fully connected layer is at the end, which is something that we inherited from MLP. It's placed before the classification output of the CNN, because ultimately image classification is what we are doing at the very core level. And this is just used to flatten the results. So it's like the finishing line just before you finalize everything and get the results out. So that is how it comes into the picture. Now, if you see this image, you basically it's just an overview of how you connect the filters together. So if you see on the left, it's like a 3 by 3 filter and a black and white image, and if you see on the right, that's a corresponding thing for an RGB image. Now, just to sum everything up, here is I mean, it's a huge, complicated example to see, but it's not as complicated. Every CNN layer is basically learning the filters of increasing complexity. So if you see at the lowermost level here, it's just shapes that you're learning. Then you improve those shapes in the next layer. So the first layer basically just does detection of edges and corners and some basic shapes. The middle layer learns the filters and detects parts of objects. For example, if you can possibly make out like parts of eyes or ears, specific features, specific parts of objects. And the last layer is which finally does a higher representation for you and allows you to recognize full objects in different shapes and different positions. So, I mean, that's CNN in totality as far as the technical details are concerned. Coming to the applications of CNN, which are immense and extensive in the sense that if we start with the image classification is the core task that CNN does, as we've been discussing all this while. So if we see the different other, I mean, sets of applications that fall under this image classification domain, there are many search engines and recommender systems and social media applications. So image recognition and classification is basically, you can say it's like the primary field that CNNs cover in terms of the application domain. It is also one of the use case that's, that backs many one of the most effective domains as far as AI impact is concerned, which is healthcare. So medical imaging and medical image computing, the backing up of it largely falls in the domain of image classification. Now, the purpose of convolutional neural networks and their usage for image classification is, what you try and do is you deconstruct an image and you identify its distinctive features. So for that, what you do is that the system needs to use a specific classification algorithms, uh, and you reduce the description of its essential credentials in such a way that it can help you identify specific things. For example, if you go to if you go back to the social media example, then identifying the face is one thing, and then tagging that face to a specific person, which is identifying the credentials and matching those credentials with another image credentials, is the second thing. Now, how is it that the whole process is done? The whole process is basically, I mean, if we talk about image tagging algorithms, which is the most basic type of image classification, then the image tag is basically a word or a word combination that describes the image. Image tagging is not just about the social media tagging, it's also about image caption generation, for example, which is a combination of CNN and RNN. So you basically identify, classify it into a word or a group of words, and then you derive a natural language equivalent of this. So that is where RNN comes into picture. It's something that we'll discuss in the next session. So Google and Facebook and Amazon, they extensively use this technique in the sense that, I mean, I have, I think this is something which has become very common these days. If you're looking for something in Google, uh, people find it easier to look at the image search and find the image, and then correspondingly look at the article than to read through the article. Now, visual content is easier to analyze for us humans than textual content. So that is how, and that is why image search and using image as a part of the search engine is so important to Google, and that is where CNN is extensively used. Then Facebook, as something we've been, I mean, discussing throughout the presentation, is for tagging purposes, for finding the right tag for the right person, uh, things like those. So uh, that is where Facebook uses it, and Amazon uses it for product recommendations, so things you might like. So it's not just about the content description. For example, you are looking for shoes, so it'll recommend you all shoes. There's a lateral algorithm that works, a CNN based algorithm, which works like this: that if you've chosen a red colored dress, there's a higher probability that you're also looking for a red colored shoe, or you're looking for a matching colored bag, for instance. So this kind of an image based recommendation is what is supported by image classification or CNN based image classification. Then visual search is, I mean, reverse image search is something that's really, I mean, it has improved by leaps and bounds in the recent past, thanks to the kinds of advancements that have happened in CNN. Image search isn't 100% accurate until now. It and would require a lot of advancements in terms of CNN, and it's something which is actively being seen as a research area of potential. Um, so and most of the research in this area, because Google aces the search engine domain, most of the research in this domain is performed by Google, as far as the industry is concerned. Finally, recommender systems. Recommender systems is, I mean, like I said, commonly used by Amazon. It's also used by Pinterest, where they basically do, I mean, tagging and matching, and a lot of it is also used in, I mean, if you see, you are recommended tags on Instagram, or you're recommended tags on most of the post-based social media portals that we have today. And how do they come up? It's not just about the content that you've put, it's also about the image that you've put, and they try and improve and tune the recommendation on the basis of the image classification that's running at the background. Now, another set of, I mean, now this is something that I have majorly discussed, which is deconstructing the image and looking at the essential credentials and the applications, which is image tagging, visual search, and recommendation engines. Now, another class of applications that is very, very widely used in terms of computer vision techniques as well, and in terms of their business applicability. So it's like an advancement that is rapidly occurring in the technical field, and it's highly backed by the business domain because of its wider applicability in the product market. Now, how is it that And why is it that it actually requires a mention? It requires a mention because it's very like image recognition, but it's like a subset of image recognition where it deals with more complex images. So now, um, an image might not just have human faces, it might have a dog as well, a cat as well, or a flying bird over the top. So when you have multiple kinds of objects in an image, the complexity of facial recognition increases by a lot of by leaps and bounds, I can say. Because I remember there was this project with I once had a chance to interact with a researcher who was working on this project where he was identifying how you can differentiate between a pigeon from another pigeon. The features are almost impossible to differentiate. So you cannot differentiate one pigeon from another pigeon. That's a problem that escalates with human beings, with in particular cases where, for example, Koreans do not have a lot of disparity in their facial features per se, in the way that we have designed our algorithms, because they're majorly designed by the West. So where there's a disparity in features at that level. But for people coming from Oriental or South Asian countries, most of these facial recognition systems may not work as well as they work for the rest. So generic form of facial recognition is something that we're still striving to achieve as a research community, and that is why it receives the mention that it does. Now the difference, if we talk about image recognition and facial recognition, obviously because now we have multiple objects, the image complexity increases, operational complexity of the algorithm correspondingly increases. So the first part remains the same. You detect objects. So object recognition is the first thing that you're going to do. The shape of the face and the features, all of that needs to be recognized. Now, whether that's for humans or whether that's for any other kind of, say a dog or an animal, will also have a face. So faces need to be recognized. That's the first basic thing that you do. Now, then what the second aspect, because it doesn't stop here for facial recognition, you need it's something more complicated and goes into the let me see, let me just check chat if someone's saying anything now. Okay, so the second step is once you have the features, you further analyze the features for essential credentials. Is again something that we were doing previously. What is the next thing, and more importantly, which gets added up in the facial recognition part, is that you need a sum of these credentials now. You need to calculate them for image data perception. And this process involves studying many samples and studying different samples in different contexts. For example, a human face can be, if you see most of the facial recognition systems that are there on the mobile phones these days, if you're using advanced mobile phones, or depending upon the kind of technologically empowered systems you're using. But if you wear sunglasses, it'll still recognize your face. If you look but there are going to be limitations. For example, if you're not looking at the camera, if your face is partially visible, the facial recognition system might fail. So these challenges of increased complexity need to be trained, require the CNN to be trained in a manner that it can accommodate for these variations, it can accommodate for these extremities, and for this you need adequate data for training, because the one of the biggest challenges with deep learning is that you need a lot of data to train the system. So now, if we look at the applications of this, then majorly, it's classified into two categories. One is social media networking, and another is entertainment. When we talk about social media, it's like again, if we go back to a conference picture or a family picture where you have a lot of people with, I mean, they have to be, they are all different with the same set of features at the naive level, the same set of features with different credentials. And there might be, I mean, um, might not be human faces as well. Like there can be dogs and cats involved in the picture. So identifying all of that. So that's how social media and social media networking involves applications like these. And then as far as the entertainment part is concerned, if all of you, and I'm assuming all of you must have used all the filters that are available with Facebook Messenger and Snapchat these days. So identifying the feature, applying a filter onto that feature in real time, and then, as you probably, I mean, you change your position, the filter accommodates itself to ensure that it's placed correctly. So that's the kind of application that facial recognition has advanced into. So it's not just about unlocking your phone anymore. It's about, putting video filters on the go into applications like Messenger or into applications like Snapchat. So that's the kind of applications that this has. Now, the next part is optical character recognition, and this is something that's found a lot of applications, particularly in the document digitization domain. Optical character recognition at the very core level is basically identifying characters and images. So it's like a mix of image processing and then converting it into a natural language format, or identifying the character or a sequence of characters. So basically, I mean, at the very core of this technology, it's designed for written and print simple processing. So in the face recognition context, like we spoke, which includes a complicated process of, you can have a person moving and the filter needs to move with the person. There are specific challenges associated with OCR processing as well. So the complexity of OCR comes from the fact that it is not pure computer vision. It is computer vision plus natural language processing. So, like I said, it's you just don't need to identify something; you need to contextualize also. So it adds another layer of processing to it. Now, how is it that it works? Generally, the first step is image recognition at the core. So you identify, recognize what is the written character, you identify the character. The second step is that you identify the credentials of a character. So, for example, I mean, you can write S in multiple ways. Some people just write S, some write it in a more cursive manner. So identifying S from that image, uh, identifying the structure, and then putting it, contextualizing to say that it is the character S. This is the second step. So identifying the credentials. When I say identifying the credentials, it is identifying the context. It is identifying that that identified shape is S. It corresponds to S. Same as with all of the other letters that are there, or the numerals, or the special characters. Um, so that becomes the second step of OCR based image processing. The third step would be to find the respective character encoding for it. For example, ASCII coding for it. Now, why do you need that? We need that because we need that to convert. I mean, when we transition from computer vision to natural language processing, we need to now work in terms of ASCII coding, the ASCII codes. So that becomes the third step. Now, the fourth step is that the recognized characters are compiled into a text, and then finally the visual layout of the text is presented. Now, examples of this are in legal, banking, insurance, document digitization, ways where you try and identify signatures. So you can, I mean, automatically identify if a signature belongs to a person or not. So applications like those. Now, the last class of applications that I'm going to cover as part of this is medical image computing. And it's something that I think has been covered extensively in the past few sessions that you've had. But just to give you an overview, I mean, healthcare is an industry which, I mean, any technology that you want to really test, you put it to use in the healthcare industry, and that's how you prove the viability of any technology. So with artificial neural networks or CNNs, this is again no exception. And medical image processing and medical image computing is extensively, it's like a very, very big, huge, large, mammoth level part of application set that CNN supports, in the sense that MRI images and CD images that you commonly get, and then, you know, creating any kinds of predictive analytics around the features that are extracted from them, assessing the risk, like I've mentioned in the applications here, drug discovery, which is a very complicated and cost intensive process, is something that neural networks simplify, reduce the amount of time that's required for drug discovery. And this field has really picked up in the current context of COVID-19, where there's this urgent need to, get a drug for it, so that all the problems around us can be sorted out as quickly as possible. Finally, precision medicine is another very, upcoming field, in the sense that and a very challenging field, because every human being, you cannot really classify humans even on the basis of their genetic makeup. The interactions and the response to drugs is very, very different for every person. And personalized medicine and precision medicine, getting to that level in dosage and formula that's very specific to that person is very challenging. The biggest challenge in this particular field is that usually, testing of these becomes really challenging, in the sense that you need a lot of ethical clearances for them. Okay, so the two use cases that I intend to give as part of the workshop is something, the files for which I will share. And if we get time in the next session, I can give you a walkthrough, is the image classification, which is a CIFAR 10 data set. It's a commonly used data set. It has some 6,000 images spread across 10 categories. And basically what you have to do is you have to create a convolutional neural network that can, I mean, whenever it's given a new image, you should be able to classify the image into one of the categories. So that's the basic task. And second is text classification, which is basically a sentiment analysis task based on a movie data set. So we're basically, in the Jupyter notebook that I will share, we're using a pre-trained model, and we're just using that to test the accuracy. Um, with most deep learning algorithms and architectures, it's the same with CNN. The number of epochs, as you increase the number of epochs, as you diversify and improve the data set that you're using, the accuracy will automatically improve. So, and whenever you're working with image data set, the amount of time that it requires the model to train is sufficiently high. So, I mean, when you put the number of epochs as, say, 50, um, go have a coffee and, come back in 15-20 minutes, because it's going to take a lot of time to train. So that's about use cases. In the next session, we'll probably talk about recurrent neural network. We'll go through the use cases and everything, the technical and the application aspects of neural network. So that's probably all I have for this session. And I think it's been 1.5 hours. Okay.
Any questions from the participant? You can mute.
One thing that I want to ask is, how do you want me to share those files? Is there an email ID where and you can share with the participants, or do you want me to share it here? I don't know if it supports file sharing. If you can, give me an email ID, I'll send you two zip files for this session and the next session, then you can share it with the participants.
Okay, ma'am.
Just send me the email ID whenever you can.
Chat we provided, madam. We provided in the chat.
Okay, I'll share it here. Right. So what that zip file has is it has the data and it has the um, okay. I've got a lot of email IDs. Which one?
A comma 94. The first one is
A Kumar. Okay. Okay, I'll send it to this. So it has the data set and it has the Jupyter notebook. So you can, try it out for yourself.
Wow.
Okay.
Okay, ma'am. Thank you. Thank you.
Okay, we'll rejoin in 1 hour, I think.
2:30 at 2:30.
It's 1 hour away, right? I am 4.5 hours behind you. So it's 9 o'clock here right now.
Now it is 1:30, madam, here.
Okay.
1:38, 1:40.
Okay. 1 hour from now. Okay. Okay, see you.
Thank you. Bye.
Okay, thank you, ma'am. Thank you.
Right. You're welcome. Bye-bye.
To all the participants, we will rejoin at 2:30. Thank you, one and all. Have a nice lunch and then rejoin again.
Thank you, ma'am.